How did fixing a broken equation accidentally create quantum mechanics? You see, Max Planck wasn't trying to revolutionize physics back in 1900. He was just trying to fix a really annoying math problem. These are the 10 breakthroughs that led to quantum mechanics, and this is number 1, Planck's accidental quantum. You see, back in the day, classical physics had a major issue with black body radiation. This is how hot objects glow. According to the classical equations, a heated object should give off infinite amounts of energy, especially at short wavelengths, especially in the ultraviolet region. This was called the ultraviolet catastrophe because it was obviously wrong, because hot objects don't actually emit infinite amounts of energy. Now, Planck was trying to fix the equations. So instead of letting energy be absorbed and emitted in any amount, he tried a different approach. What if it only happens in fixed size chunks? And he called these chunks quanta. Suddenly the equations worked. The theoretical curve matched what was actually observed, so there was no more ultraviolet catastrophe. But the interesting thing about all of this is that Planck didn't actually think that these quanta were real. He just thought it was a mathematical workaround to make the numbers behave. So he spent years trying to find a way to get rid of the quanta and return to classical continuous energy. But he couldn't. So whether he meant to or not, Planck had opened the door to quantum mechanics. And then 5 years later, Einstein would prove that these quanta were real. But that's for the next episode. Follow along for more. Stay nerdy. How did Einstein's Nobel Prize discovery lead to quantum mechanics? You see, Einstein didn't win the Nobel Prize for relativity. Lots of people think he did. But he actually won it for proving that light is made of particles. These are the 10 breakthroughs that led to quantum mechanics, and this is number 2, Einstein's photons. So the photoelectric effect had been puzzling physicists since the 1880s. When light hits certain metals, it kicks out electrons. Now, classical physics had a clear prediction. Brighter light should mean more energetic electrons. But that's not what experiments showed. The energy of the ejected electrons depended only on the color of the light, or its frequency. It didn't care how bright the light was. So faint blue light could knock out some pretty high energy electrons, whereas really bright red light, no matter how intense it was, did nothing at all. Now, Einstein's explanation was pretty radical for the time. Light isn't just a wave, it's made of particles, which were later called photons. Each photon carries a fixed amount of energy determined by its frequency, E equals hf. This is where h is Planck's constant. Now, when a photon is absorbed by an electron, the electron gains all of the photon's energy. If that energy is more than the minimum energy needed to escape, the electron leaves instantly. If it's not, nothing happens and the energy gets dissipated as heat. This wasn't just a clever idea. It was a complete rethink of what light is, wave and particle simultaneously. Now, in the last video, we talked about Planck's reluctant use of quanta as a math trick. Einstein said these energy packets aren't just maths, they're real. He proved that Planck's quanta weren't a workaround. They were a fundamental property of nature. So the photoelectric effect is why we have things like solar panels and photocopiers and image sensors today, all based on light behaving like particles. But if energy comes in discrete packets, what did this mean for the atoms themselves? Now, by 1913, there was a serious problem with how we thought atoms worked. That's for the next episode. Stay tuned for more and stay nerdy. Why don't electrons fall towards the center of atoms? Now, if classical physics was right about particles, then you and I would not exist. Atoms would be impossible. These are the 10 breakthroughs that led to quantum mechanics, and this is number 3, Bohr's quantum orbits. Now, by 1913, we knew atoms had a dense nucleus and they were surrounded by orbiting electrons. But we looked at them like tiny solar systems, and there was a pretty massive problem with this. You see, any charged particle that moves in a circle should constantly radiate energy. An orbiting electron should lose energy and spiral into the nucleus in about 10 to the minus 10 seconds. Every atom in the universe should have collapsed billions of years ago. But atoms are stable, we know this. So either the model was wrong or the physics was wrong. Now, Niels Bohr tried something different. He kept the orbital model, but threw out the idea that electrons could have any orbit they wanted. Instead, he proposed that electrons can only occupy certain fixed energy levels, specific orbits with specific energies. They can jump between levels by absorbing or emitting energy, but they can't just sit anywhere in between. So when electrons jump down to lower levels, the energy difference gets released as light. And this explained why atoms emit very specific colors, because these colors match the energy differences between the allowed levels. For hydrogen, Bohr's model worked perfectly. The calculated wavelengths matched the observed spectral lines exactly, but it only worked for hydrogen. Heavier atoms were still a mess, and nobody knew why only certain orbits were allowed. Bohr's model wasn't the complete quantum theory, but it was the first time someone said, maybe energy levels in atoms are quantized, and got the maths to match the reality. So it saved physics from the collapse problem and opened the door to thinking more about quantized systems. But atoms had more surprise in store. In 1922, an experiment would reveal something completely unexpected. But that's for the next episode. Follow along for more and stay nerdy. How did a failed experiment discover quantum spin? In 1922, Otto Stern and Walther Gerlach expected to see a blur. They got 2 dots instead. These are the 10 breakthroughs that led to quantum mechanics, and this is number 4, the discovery of spin. Stern and Gerlach were looking at angular momentum. This is the physics of spinning and orbiting. Now, they wanted to test if it might be quantized like energy seemed to be. Their experiment was fairly simple. Fire a beam of silver atoms through a strong magnetic field and see what happens. Now, if angular momentum could point in any direction, the magnetic field would spread the beam into a continuous blur. Some atoms deflected one way, some another, in a smooth gradient. If angular momentum was quantized, they might see a few discrete spots instead of a blur. What they actually got was exactly 2 spots. The beam split cleanly in half. This made no sense with what they knew about orbital motion. Even if angular momentum was quantized, they should have seen more than 2 values. Now, it took 5 years to figure out what they discovered, and they discovered electron spin. Now, this is not spinning like a tiny ball on its axis. This is something more fundamental. It's an intrinsic property that has no classical equivalent. Every electron has spin 1/2, which can point either up or down relative to a magnetic field. That's it, just 2 options. The Stern-Gerlach beam split because half the atoms had electrons with spin up and half with spin down. Now, spin isn't motion, it's a purely quantum property. So electrons aren't actually spinning, they just have this built-in angular momentum that comes in these 2 values. And this experiment forced physics to accept that particles have properties that are entirely different to what we are used to, and that we cannot describe using classical physics. But if particles could have strange quantum properties, What about their fundamental nature? And in 1923, someone asked a very important question. But that's for the next episode, so follow along for more and stay nerdy. Can particles behave like waves? In 1923, Louis de Broglie asked a simple question. If light can act like particles, can particles act like waves? These are the 10 breakthroughs that led to quantum mechanics, and this is number 5, matter waves. So Einstein had just proved that light waves could behave like particles called photons. De Broglie flipped it around. What if electrons, protons, even a tennis ball had wavelengths associated with them? So he wrote down a fairly straightforward equation. Lambda equals h over p. Now lambda is wavelength, h is Planck's constant, and p is momentum. So depending on the momentum, that will determine the size of the wavelength. So for a tennis ball, the wavelength is unimaginably tiny. It's about 10 to the minus 34 meters. It's like 1 over 10 to 30. I can't tell. There's lots of zeros. Completely negligible. But for an electron, the wavelength becomes fairly significant. It's similar to the spacing between atoms in a crystal. Now this was testable. If electrons really had wave properties, they should show interference and diffraction just like light waves do. Now the proof came with the double slit experiment using electrons instead of light. When you fire electrons at a screen with 2 narrow slits, you don't get 2 lines like you'd expect from particles. You get a wave interference pattern, alternating bright and dark bands. Even more strange, if you send electrons through one at a time, the interference pattern still builds up. Each individual electron goes through both slits simultaneously, and the only way this works is if the electron is a wave that can interfere with itself. This established wave-particle duality as a fundamental property of matter, not just light. Now, particles are quantum objects. They show wave-like or particle-like behavior depending on how you interact with them. But wave-particle duality raised a new question. Why don't all these quantum waves collapse into the same state? And the answer to this would change everything. But that's for the next episode. Follow along for more. Stay nerdy. What stops the universe from collapsing into a single point? Wolfgang Pauli discovered a rule in 1924 that literally keeps you from existing as a puddle of collapsed matter. These are the 10 breakthroughs that led to quantum mechanics, and this is number 6, the exclusion principle. The problem here was, if electrons can occupy any energy level, why don't they all just fall down into the lowest one? Why do atoms have structure instead of every electron piling up in the ground state? Now, classical physics had no answer to this question, but the periodic table suggested that electrons definitely do arrange themselves in shells, filling up in a very specific order. Pauli proposed something new. No 2 identical fermions, which are particles like electrons, can occupy exactly the same quantum state. Now, this isn't a force that's pushing them apart. It's a fundamental rule of nature. If one electron is in a particular state, which is defined by its energy, its spin, its orbital characteristics, then no other electron can be in that exact same state. So electrons have to stack up in different energy levels, different orbitals, different spin orientations. They're forced to spread out. This is the Pauli exclusion principle, and it explains the entire structure of atoms. First electron goes in the lowest state. Second electron can join it if it has the opposite spin. And then the third electron has to go up to the next energy level, and so on. This creates the electron shells that give elements their chemical properties, and it's why hydrogen acts differently from helium, why carbon can form complex molecules, and essentially why chemistry exists, at all. So without the exclusion principle, every electron in the universe would just collapse down into the same lowest energy state, so there'd be no atomic diversity and no life.
Now, the exclusion principle isn't just about electrons. It applies to all fermions. It's what keeps neutron stars from collapsing into black holes, and it determines how matter behaves under extreme conditions. But by 1925, physics was still like a mess of half classical and half quantum ideas. Someone needed to start from scratch. But that's for the next episode. Follow on for more and stay nerdy.
What do you think would happen if you stopped trying to see what atoms look like? Werner Heisenberg made the breakthrough that created quantum mechanics 100 years ago this month by doing something completely new. He stopped trying to visualize what atoms look like. These are the 10 breakthroughs that led to quantum mechanics, and this is number 7, matrix mechanics. By 1925, atomic physics was a total mess. Bohr's model worked for hydrogen but failed for everything else. Electron orbits, spinning particles, wave-particle duality, none of it made like intuitive sense. Every attempt to create a visual model of what was really happening inside atoms just led to a bunch of contradictions. So Heisenberg took a different approach. He decided to ignore what atoms might look like and focus only on what could be directly measured. What can you actually observe from atoms? So the frequencies and intensities of light they emit when electrons transition between energy levels. Heisenberg built a mathematical framework based entirely on these observable quantities, using just arrays of numbers representing the probabilities of transitions between quantum states. He'd invented matrix mechanics without realizing it. But when he showed his work to Max Born, Born recognized the mathematical structure immediately. So this wasn't just a new theory, it was a completely new kind of physics. One that didn't rely on classical intuition about how things should work. And from this came everything else. Schrödinger's equivalent wave mechanics, the uncertainty principle, probabilistic quantum states, and the modern understanding of atoms. All because a 23-year-old physicist decided that maybe we don't need to see what atoms are doing. Maybe we just need to predict what we can measure. But Heisenberg's abstract matrices weren't the only way to do quantum mechanics, and a year later, someone found a more familiar approach. But that's for the next episode. Follow along for more and stay nerdy. Can two completely different theories describe the same reality? In 1926, Erwin Schrödinger created what looked like a completely different quantum theory. Instead of Heisenberg's abstract matrices, Schrödinger used familiar wave equations. These are the 10 breakthroughs that led to quantum mechanics, and this is number 8, wave mechanics. Now, his approach started with the de Broglie matter waves. If particles have wavelengths, maybe you can describe them using wave mechanics instead of particle mechanics. Schrödinger developed a wave equation that treated electrons as three-dimensional standing waves around atomic nuclei. It's kind of like sound waves in a musical instrument, only certain frequencies could exist, and these became the allowed energy levels. It was a more visual method and it used more familiar mathematics, so you could actually picture what was happening. Now, at first, physicists weren't really sure how Schrödinger's approach related to Heisenberg's. They looked completely different mathematically, and this kind of created some uncertainty in the community. Were these like competing theories, or was it something else? And the answer did come pretty quickly, within months actually. It was proven that wave mechanics and matrix mechanics were mathematically equivalent. They're just different ways of describing the same underlying physics. You could solve any quantum problem using either Schrödinger's waves or Heisenberg's matrices, and you would get identical results. Now, the wave function in Schrödinger's equation contains the same information as Heisenberg's probability matrices. The mathematics looks completely different, but the physics is identical. And this was really reassuring. It meant quantum mechanics wasn't arbitrary. There was actually something fundamental being described, even if it could be approached from different mathematical angles. Now, today, we use whichever approach is more convenient for the problem that we're looking at. So if you're looking at atomic structure, you might use Schrödinger's waves, or if you're looking at particle interactions, you'll probably use Heisenberg's matrix methods. But having two equivalent theories raised a crucial question. What do these wave functions actually represent? But that's for another episode, so follow along for more and stay nerdy. What does a quantum wave actually mean? Max Born solved the biggest puzzle in quantum mechanics. What does the wave function actually mean? Now, these are the 10 breakthroughs that led to quantum mechanics, and this is number 9, the probabilistic interpretation. By 1926, everyone agreed that Schrödinger's wave equation worked. It gave the right energy levels, predicted atomic spectra, and matched all the experimental data. But nobody knew what the wave function actually represented. Schrödinger initially thought that it was the electric charge density, like how much charge was spread out in space. But this led to contradictions with experiments involving individual particles. Born proposed something else. The wave function doesn't describe what the particle is doing, it's describing the probability of finding the particle in different states when you measure it. Specifically, psi squared gives you the probability density, the likelihood of finding a particle at a particular location or in a particular state. This interpretation solved several problems at once. When an electron goes through both slits in the double slit experiment, the wave function describes the probability of finding it at different points on the screen. The interference pattern emerges because probabilities can interfere with each other. When you measure a particle's position, you don't just observe a pre-existing location. The measurement forces the wave function to collapse to a definite state, giving you one specific outcome from the range of possibilities. Now, this probabilistic interpretation became a key component of what would later be called the Copenhagen interpretation of quantum mechanics. So quantum mechanics doesn't tell you what will happen. It tells you the odds of different outcomes. Nature isn't deterministic at the quantum level, it's fundamentally probabilistic. Einstein famously objected to this, saying God does not play dice, but Born's interpretation has withstood nearly a century of experimental tests. So this led to a big question. If quantum mechanics is fundamentally about probabilities, what does this mean for what we can actually know about reality? But that's for the next and last episode. So follow along for more and stay nerdy. Is there a limit to what you can know about reality? In 1927, Heisenberg discovered something disturbing about reality. There are fundamental limits to what you can know about a particle. These are the 10 breakthroughs that led to quantum mechanics, and this is number 10, the uncertainty principle. The uncertainty principle states that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. Now, this isn't about measurement problems or like clumsy instruments or anything. It's built into the fabric of reality. The mathematical relationship is delta x times delta p is greater than or equal to h over 2, where delta x is the uncertainty in position, delta p is the uncertainty in momentum, and h bar is Planck's constant. Now, why does this happen? It comes from the wave nature of particles. To measure a particle's position precisely, you need to use high energy photons with short wavelengths. But when these photons hit the particle, they transfer momentum and knock it around. The more precisely you try to pin down where it is, the more you disturb its motion. And conversely, to measure momentum precisely without disturbing it, you need low energy photons with long wavelengths. but long wavelengths can't determine position very accurately. Now, there's also an energy-time uncertainty relation, which is delta E times delta T is greater than or equal to h bar over 2. And this is what allows for quantum fluctuations, which are brief violations of energy conservation that create virtual particles and drive processes like radioactive decay. The uncertainty principle, it's not a limitation of our knowledge. It's a fundamental property of quantum systems. Particles don't have definite position and momentum simultaneously. These properties are complementary. You can measure one or the other precisely, but never both. And this complementarity, combined with Born's probabilistic interpretation, completed the quantum mechanical world view. Nature is fundamentally uncertain, and there are limits to what can be known. Now, these 10 breakthroughs didn't just create a new theory, they shattered our understanding of reality itself. In just 25 years, physics went from believing the universe was predictable and mechanical to accepting it's probabilistic and strange at its core. Thanks for following this series along. I will be back soon with a new topic. Follow if you want science nerd content and sci-fi nerdness and stuff. So cool. Thanks for hanging out. Stay nerdy. Bye.